Bismillahirrahmanirrahim. Assalamualaikum and good day everyone. So inshallah we are going to enter our chapter 12 part 2 entitled as Elasticity. So if you refer to the diagram that I put it here, it's rubber band, isn't it? For sure we have experienced the elasticity within our rubber band during our kids time. Alright, but now we are going to look at more detail about the elasticity in matter. Alright, it's not only a rubber band, for example, has the elasticity. Actually, solids materials also has elastic properties. Alright, for example, bricks, road, cement, and also metal, copper, aluminium, zinc. Okay, so all the solids also has the elastic properties, but then the way it reacts, okay, the degree of the elasticity is varied, is very small compared to rubber band, for example, just now. So it is depending on the stress applied. Okay, so based on observation, stress applied on solids is directly proportional to the strain. What is stress? If you still remember, stress is in general is pressure is equivalent to F over A, isn't it? The F must be perpendicular to the A. This is a common definition of stress. What is strain? Strain is actually degree of the deformation. Produced due to the stress applied. Right. So when we have a proportionality like this, okay, stress is proportional to the strain. Okay, so to put it in a formula pattern, stress is equivalent to mathematical expression. Okay, must be a modulus, right? Okay, must be a constant, okay, times with a strain. Okay, so the constant here is known as elastic modulus. Right? So constant here is the elastic modulus. So different deformation, different degree of deformation. Okay, certain object elongate, certain object deform in term of shape, certain object deform in term of volume of it. Okay, so the different type of strain, okay, give different elastic modulus to us, right? So rearrange this mathematical expression. We're going to have elastic modulus equivalent to stress over strain. So we have three kinds of elastic modulus to be considered as your syllabus. The first one is Young modulus. It measures the resistance of a solid to a change in its length. So Young modulus is about length, change in length. And second one is shear modulus. Shear modulus measures the resistance to motion of the plane within a solid parallel to each other. Alright. So next one will be, or in simple, shear modulus talking about change in shape. Alright. The third one is bulk modulus, measures the resistance of solids or liquids, okay, to changes in their volume. So when we talk about length, okay, then we are going to refer to Young modulus. If we're talking about shear modulus, okay, so it's referring to the planes within the solid, okay, or simple shape, change in shape. Right. Then bulk modulus is referring to the change in the volume. Right. So let's take a look on detail of the Young modulus, elasticity in length. whereby we are going to refer to the elasticity in length. Right, the symbol for Young modulus is capital Y. Okay, is equivalent or proportional to the tensile stress over tensile strain. Okay, we call it tensile when it's involved elongation or compression in terms of length. Alright, so tensile stress is equivalent to F over A. Right, and tensile strain is equivalent to delta L over L initial, original L, change in length, okay, over the original length. Okay, so because we have to understand that strain is the degree of deformation. So in terms of length, what is the deformation? What is the change or strain happen or deformation happen, which is the length. Initially, okay, this rod having L initial, and then we apply force, okay, to the cross section of this metal or beam. Okay, then due to the applied force, okay, there is delta L happen. Okay, so the strain, the degree of deformation will be delta L over L initial. So you can see here, the unit for Young modulus here is equivalent to the unit of stress, okay, which is Pascal or Newton per meter square, because the unit of the strain is cancelled out because it's a ratio of the same units. So let's take a look on this. Okay, this is a graph where the behavior of the stress versus strain, right? So initially, okay, the object going to experience elastic behavior, okay, almost proportional, okay, between stress and strain. Okay, so within this region where the response is proportional, okay, we call it, okay, the object is experiencing elastic behavior. Alright, but after it reach, okay, elastic limits, okay, when you keep on increasing the force, okay, the stress, alright, what will happen? Okay, it reach one point where we name this point as elastic limits. When it's already reached elastic limits, okay, the response going to be, okay, slightly increased but almost reaching a constant value. After it goes beyond the elastic limit, okay, means that the object now not going to return to its original shape. Okay, within this area, elastic behavior, yes. After you take out the stress, the object going to return to its original length or shape. But when it reach elastic limit here, beyond the elastic limit here, the object not going to be returned to its original length or shape anymore. Okay, because it's already reached its elastic limit. Alright, so it's not elastic anymore in simple way. If you keep on increasing the stress, okay, the object going to reach one point where we have breaking point. What does that mean? The object going to be tear. Okay, it's going to be damaged. Right, so the object going to break in simple word. Alright. Second one is shear modulus. Shear modulus, okay, also known as elasticity of shape. Okay, so the symbol is capital S. Okay, it's equivalent to shear stress over shear strain. Okay, so stress still F over A, and the degree of the deformation or the strain, since we are talking about change in shape. For example, this book, Okay, our textbook here is placed on the table. We apply a force parallel to the surface of the book. Okay, what will happen? There is a frictional force, okay, at the bottom part of the book, okay, due to the contact with the rough surface, which is the table here. Okay, so since the possible motion of the book will be to the right, okay, so friction going to be to the left. Due to the forces which is I've applied and friction which is parallel to the cross section of the book, all right. So the shape of the book instead of box here, okay, is going to be slightly to become trapezium, the cross section of the book. Okay, so the original cross section of this book is this one. Okay, then after we applied force, okay, I've applied, okay, to the top surface of the book, and friction gonna be at the bottom of the book. Now the cross section of the book going to be changed into a trapezium, right, slightly. So okay, now we have change in shape in overall. Okay, so the strain will be measured, okay, how much, okay, the differentiation, how much, okay, delta x axis or produce, okay, which is shifted, okay, from the original position, right, over the original height of, okay, this section. So this is the shear strain, delta x over delta h. Okay, so it means that the shape of the book is changed. That is why the name of shear modulus also known as elasticity of shape. Alright. Okay, third one, bulk modulus. Okay, where we have volume elasticity. So bulk modulus is defined as volume stress over volume strains. So the dashed line here, okay, is the original volume of this object. Okay, when this object, the cube, undergoes a change in volume but not change in shape, still a cube. Okay, so this is the new volume of the cube just now. Okay, so we have this kind of situation, we are going to refer to bulk modulus. Bulk modulus is defined as stress, volume stress, F over A, okay, over the volume strain. So what did deformation happen just now? Change in volume over initial volume. But normally, okay, change in volume here will be negative amount because it is in decrease amount. Alright, so negative of this over V initial, to counter the negative happen here within the delta V here, we are going to put negative sign in front of this equation. So it might be that the pressure or the stress also change. That is why we put delta P. For example, a cube of this object firstly is in air at atmospheric pressure, and then suddenly we immerse this cube object into water. So means that the pressure or the stress experienced by this cube already changed. So change in pressure is the volume stress, okay, over volume strain, which is change in V over V initial. And normally change in V has negative sign, so we put negative sign in front of this equation to counterback the negative sign within the delta V. Right, so listed here in this table, okay, is the elastic moduli values for each metals. For example, we have tungsten, we have steel, copper, brass, aluminium, glass, quartz. Okay. So for water and mercury, we don't have Young and Shear modulus, but we have Bach modulus. Okay. Alright, let's take a look on quick quiz 12.4 part 1. Which elastic modulus describe the relationship between stress and strain for a block of iron sliding across a horizontal floor? The friction force between the sliding block and the floor causes the block to deform. What do you think? Whether it's Young modulus, Shear modulus, Bach modulus, or none of the choice? It's actually shear modulus because, okay, it's described between stress and strain for a block of iron sliding. That is the word. Sliding across a floor. Okay, horizontal floor. The friction force between the sliding block, okay, causes the block to deform. So we can imagine that, okay, a block originally like this, okay, and then when it is sliding, it's going to be, okay, more or less like this. So if this is the case, then we are going to see shear modulus, which is change in speed due to the friction here. Okay, right. Which elastic modulus describe the relationship between stress and strain for a trapeze artist swinging through a circular arc? At the bottom of the swing, the wires supporting the trapeze are longer than when the trapeze artist simply hangs from the trapeze due to the increased tension in them. So, I think this is about elongation, right? So, by right, it's involving Young modulus because it's about the string is elongates, okay, or it is increased in length. Which elastic modulus describe the relationship between stress and strain for a spacecraft carrying a steel sphere to a planet on which atmospheric pressure is much higher than on the Earth? The higher pressure causes the radius of the sphere to decrease. So this is about Bach modulus because it's change in volume due to the change in pressure. Okay, so pre-stress concrete. Okay, see, this is understanding. By understanding the concept of elasticity in metal or solid, okay, we can have an idea of how to make our design better. So if let's say we have only concrete, okay, when we put lock force, okay, on the top of it, okay, what will happen? We are going to see produce cracks here, okay. But when we put steel, okay, as the reinforcing rod into our concrete, okay, even though we apply load force, what will happen? Okay, we see steel rod under tension, okay, going to support the whole concrete, so it will not crack at the bottom of it. Okay, this is why we introduce steel rod into concrete. All right. Example 12.5, stage design. Recall an earlier example where we analyze a cable used to support an actor as he swings onto the stage. Now, suppose the tension in the cable is 940 Newton. As the actor reaches the lowest point, what diameter should a 10-meter long steel cable have if we do not want it to stretch more than 0.5 centimeter under this condition? So since this is involving elongation of a steel cable, so we are going to use Young modulus is equivalent to stress F over A over the strain, which is delta L over L initial. So our interest right now is the diameter. So we are going to rearrange this equation so that our interest is the A. In A, we have the R, okay, pi R squared, right? So we know that we want to have the D. So the D is 2 times the radius of the cross section for the steel cable, okay, and our R is equivalent to square root of A over pi. This is coming from A is equivalent to pi R squared. So R itself, A over pi, so square root of A over pi. Alright, so since we want to have D is 2 times R, which is 2 times square root A over pi. And our A itself is FL I initial over Y delta L. So substitute it here, okay, you will get, okay, the value of diameter is equivalent to 3.5 millimeter. Alright, example 12.6, squeezing a brass sphere. A solid brass sphere is initially surrounded by air, okay, and the air pressure exerted on it is 1 times 10 to the power of 5 Newton per meter squared. This is the normal atmospheric pressure, okay. This is also equivalent to 1 atm. The sphere is lowered into the ocean to a depth where the pressure is 2 times 10 to the power of 7 Newton per meter squared. Okay, the volume of the sphere is in air is 0.5 meter cube. By how much does this volume change once the sphere is submerged? So the question asking for delta V. Based on bulk modulus formula is negative delta P over delta V over V initial. So now we are going to rearrange the equation, okay, which is our delta V is equivalent to V initial negative of V initial delta P over bulk modulus. Substitute the rest of the information given to us, then we will know that delta V is negative 1.6 times 10 to the power of negative 4 meter cube. This is the amount of the change in volume for the sphere. That's all from me. Thank you very much for watching. Do not hesitate to ask me any question regarding this lecture. Assalamualaikum.